Friends, welcome to Akulmach Live. Let me ask you, when we look up in the night sky, which celestial body sparks your imagination the most? For many, it's Mars, our intriguing red neighbor. For centuries, we have dreamed of walking on its surface and perhaps even living there. But how do we build a home millions of miles away in an incredibly hostile environment? Forget hulling tons of material across the solar system. What if I told you that the answer to our Martian housing crisis might lie in some of the Earth's oldest and most resilient life form, which is the bacteria and the fungus? We will explore today the revolutionary concept of biobuilding on Mars. We will delve into how these remarkable microorganisms aren't just surviving in extreme conditions but are actively being engineered to grow structures, turning Martian dust into durable, habitable shelters. This isn't science fiction anymore, it's rapidly developing field that could redefine the future of space colonization. We will start by understanding the immense challenge of building on Mars. Then, meet our incredible biobuilders, which is lichen and bacteria. Next, we will dive into the cutting edge research showing how they can construct real structures. Finally, we will look at the remaining hurdles and the exciting future of this technology that it holds. So, on Earth, we rely on concrete, steel, and wood. But imagine shipping a single brick to Mars, the cost is astronomical. We need to move beyond traditional methods. The sheer mass, complexity, and the cost of transporting conventional building material like large-scale Martian settlement, makes it almost impossible. Mars isn't just far; it's incredibly inhospitable. Let's consider these challenges first. Number one is radiation. Mars lacks a thick atmosphere and a strong magnetic field, meaning surface colonists would be exposed to deadly levels of cosmic and solar radiation. Our home needs to be shielded. Number two is atmosphere. Atmosphere is incredibly thin, less than 1% of the Earth's atmosphere, and mostly carbon dioxide. It offers no breathable air and minimum protection from micrometeorites. Number three is temperature extremes. Temperatures swing widely from pleasant daytime high to brutal nighttime lows, sometimes over 100 degrees Celsius in a single day. That's a fluctuation. And therefore, structure needs extreme insulation. Number four is the dust storms. Global dust storms can rage for months, coating everything, impacting everything, including solar panels, and also obscure visibility. Number five is low gravity. While seemingly minor, Mars gravity is only about one third of Earth's gravity. This affects structural design and could have long-term health implications for inhabitants if not properly accounted for in the habitat design. So all these factors means that we need to innovate, and we need to have self-sufficiency and robust building solutions. This is where the bio building comes in. The key principle here is ISRU, which is in situ resource utilization, using what's already on Mars to live and build, and what's abundant on Mars, and that is regolith, the Martian soil, and the thin atmosphere of CO2. Now let us understand what we are using here. Number one is lichen, which is the fungus, type of a fungus. So what is lichen? Let us introduce our first Martian architect, which is lichen. These aren't the single organisms, they are symbiotic marvel, a partnership between fungus and an algae or cyanobacteria. This unique collaboration allows them to survive some of the Earth's most extreme environments, from Arctic tundras to scorching deserts. The fungus provides structure and protection while the algae and cyanobacteria photosynthesize, providing food. This self-sustaining nature makes them incredible, building blocks, and also resilient and adaptable. New studies have even blasted lichens with a year worth of simulated Martian radiation in a day, and they survived. This metabolic activity in Mars-like condition is a game changer. Next, we have bacteria, specifically certain type like cyanobacteria and the filamentous fungi that works in tandem. Bacteria are microscopic powerhouse capable of incredible feats of biomineralization. Think about how limestone caves are formed, or how some bacteria can fix nitrogen. These are natural processes of material creation. We are harnessing that power in this process. The most exciting breakthrough come from combining these forces, and therefore researchers like Dr. Cognary Grace Jane and her team at Texas A&M University are developing synthetic lichen systems. This isn't about finding existing Martian life, it's about engineering Earth-based life to thrive and build our habitat when on Mars. So here how it works. Let's look at cyanobacteria. These are photosynthetic using Martian sunlight, CO2 from the atmosphere and water from the ice deposits to produce energy and oxygen. The next candidate is filamentous fungi. These fungi, fueled by the cyanobacteria, create mineral byproducts that act like natural cement. They bind the loose Martian dust, the regolith, which is the soil which is found everywhere on Mars, and it converts regolith into solid functional structure. The self-growing process is the method that we use. This symbiotic relationship means the system is largely autonomous. It needs regolith, air, light, and initial inorganic liquid medium. The bacteria and lichen secrete biopolymers that enhance adhesion, effectively growing bricks and structures without constant human intervention or supply lines from Earth. So how they build the buildings, and what is the concept and technology? Number one is 3D printing with bio ink. So how do we shape these living material into a home? The answer lies in advanced 3D printing. Researchers are developing regolith ink, a slurry infused with bio builders. Imagine robotic printers deployed on Mars, extruding their bio ink layer by layer. As the ink dries, the lichen and the bacteria activates, growing and solidifying the structure, effectively self-healing any micro leaks and increasingly durability over time. This is a radical shift from assembly to growth. Buildings aren't just built, they are cultivated. That is what these bio-built homes look like. Think domes and organic shapes which are inherently stronger and quite strong against the pressure differentials and allow for efficient growth patterns. These structures wouldn't just be walls. They could incorporate biogenerative life support system where plants grow within the habitat, recycling air, water, and waste. The living walls themselves could contribute to oxygen production and CO2 scrubbing, creating a truly closed loop ecosystem. Beyond saving mass, the advantages are profound. And number one advantage is sustainability, which means utilizing local Martian resources is important, and that will reduce reliance on Earth. Number two is self-healing and durability. Very important. Living material can repair themselves, adapting to harsh environment. Number three is radiation shielding. The density of the regolith bound by the biomaterial can provide effective radiation shielding. Number four is reduce carbon footprint. So less need for industrial processes to create material for space, even on Earth. And potential for oxygen production. So, cyanobacteria contribute to oxygenation within the habitat itself. Lastly, psychological benefit. Imagine living in a home that is alive, green, and growing on the red Martian landscape. It truly, amazing design. While incredibly promising, this technology faces significant challenges too, and before it can become a reality on Mars. Number one is scaling up. Moving from lab experiment to large scale construction on another planet is definitely a challenge. We need to first try and see how it scales up. Number two is environmental control. Precisely controlling the growth condition, which is things like temperature, humidity, light, for optimal performance in an uncontrolled Martian environment. Next is long term durability. So, we have not done any analysis, we have not done construction, so we don't have any experience in terms of durability. Ensuring that biomaterial can withstand decades of Martian condition without degradation. Next is contamination concerns. Preventing Earth microbes from contaminating Mars and ensuring the biobuilders remain contained within the structure. And autonomous operation. Developing truly autonomous robotic system for deployment and maintenance, minimizing human intervention. So, despite these hurdles, research is advancing. NASA NIAC program, which stands for NASA Innovative Advanced Concepts, is funding the project, which is now taking serious interest in this approach. This technology isn't just for Mars. Imagine its application on the moon, or even for a sustainable self-repairing infrastructure here on Earth, especially in remote and disaster-stricken areas. We could see prototype structures being tested in Martian simulation environments in the coming years, paving the way for eventual robotic deployment. Today, we are exploring tiny, resilient organisms, lichen and bacteria, and they are poised to become the unsung heroes of the Martian colonization. We have seen how they have overcome the immense challenge of the red planet, offering sustainable, self-growing, and even self-healing solutions for the future habitats. And from lab benches to the dusty plains of Mars, the vision of growing our home is no longer a dream, but a tangible future. The prospect of establishing a sustainable human presence on Mars is one of the humanity's greatest endeavor, and it's truly inspiring to think that very fabric of our Martian home could be alive, breathing, and growing with us. This bio revolution reminds us of the incredible ingenuity of life itself, and how by working with nature, even in the harshest environment, we can unlock extraordinary possibilities. So, friends, thank you for joining me on this journey to the future of Martian architecture. I am excited to see how these bio builders will shape our off world destiny. And I'm happy to take any questions you might have. Thanks for joining me today, and I will catch you again in the next one. Bye for now.